What do you feel when you see this word? For some of you in the audience, it's a word that'll trigger many different memories. For me, it brings back a range of emotions: success, frustration, anxiety, to name a few. So it's no surprise that some people on the internet have gone as far as to call math mental abuse to humans. And to be fair, I don't think we can really blame them, because math can certainly feel like that sometimes. Wouldn't you agree? So before I continue, could you please raise your hand if you've ever had a math tutor before? That's a lot of you. And I was no different. I went to one called Kumong, which became an integral, pun intended, part of my life for about a decade. And after finishing it, yes, that includes all the extra levels, I went on to complete IGCSE Maths, AT Maths, and AP Calculus BC in successive years. So I guess you can say I've had a pretty good experience with the subject. And through these experiences, I've learned that hard work is essential to completing any task. But more importantly, in my opinion, is the way that you approach and perceive the task, since it can play a significant role in changing your experience. So, let's say you were asked to design a floor with tiles, preferably of equal to similar area. You could pick any shape, or use a combination, perhaps, to completely fill it in without leaving any gaps. The question is, what would be the most efficient way that you could do so? And by efficient, we mean a cohesive design which uses the least boundary edges. So here's one way in which we could approach this. So right off the bat, we can actually rule out using more than one shape, since they would overcomplicate the pattern and would be difficult to produce. We could also rule out using irregular shapes, like these little chicken nugget-shaped blobs on the left, because when you try to fit them together, you can see that they leave gaps here and there. Now, some of you guys in the audience might be thinking, well, why don't we use a circle? After all, it's the shape with the most area for a search perimeter. Well, you would be correct in that sense, but unfortunately, as you can see, when you tile them together, they leave small gaps in between where they join together, so they're inefficient. Now that leaves us with just regular polygons. And if we're going to be using regular polygons, that means the interior angle of the shape will have to be a factor of 360, leaving us with just 3 shapes: triangles, squares, and hexagons. Any other shape, when tiling around a point, will leave a gap, which would have to be filled by a different shape or would overlap. So to continue, we can now use the area for the formula of any regular polygon being L squared times n over 4 times tan pi over n. Now, the way which we can find which shape is the most efficient is if we make the perimeter of the shapes the same, and by comparing the area. So now, the perimeter, as p, can be expressed as a number of sides times the side lengths. So we can rearrange, so L is equal to p over n. Now, if we substitute this value of L into our original area equation, we can get it to simplify to p squared over 4n times 10 pi over n. Now finally, we can substitute the values of n for each of the shapes into this equation to get the area. So for n equals 3 for the triangles, we would get 0.0481 p squared. For the squares, n equals 4, 0.0625 p squared. And finally, finishing off with hexagons, we would get 0.0722 p squared, which shows that hexagons have the greatest area, meaning they're the most efficient. So we've answered the question I gave you. Okay, I'm seeing a bit of bored faces in the audience, and you guys might have got a bit lost. But that is totally understandable, and it's exactly why math can feel hard with all the formulas that were flying around. But here's the thing. While we can show mathematically why hexagons are the most efficient, nature has figured it out long before humans did, and it's probably something that you're familiar with. I'll give you a moment to think about it to see if we're thinking of the same thing. All right, time's up. Did you guys think of this? Honeybees and their honeycombs. And with their brains smaller than a grain of rice, they most certainly don't solve formulas or plug in numbers just to figure out how to build their hives effectively. But in the end, they were able to create the best and perfect solution, which is this hexagon arrangement you see. In fact, the situation bees face is similar to the problem I gave you earlier, where the lines you see here are made from wax, and honey is what is used to be stored in it. Now, interestingly, the honey and the wax can be made from the same material, which is nectar, which bees work tirelessly going from flower to collect it. The catch is, wax is very costly to produce. It takes around 8 times more nectar than it does if bees wanted to produce the same amount of honey. So when building the hive, bees should aim to use the least amount of wax, so they can produce the most amount of honey, which is their food. Imagine you were the bee, given the same task. And so now, with the help of my assistant Grace, I'm going to show you a way which you could have approached the problem without even having to deal with numbers. So here, in this diagram, you can see a triangle, square, and hexagon of equal perimeter. And the triangle is currently filled to the brim with marbles of equal size. Now what happens if we move the marbles from the triangle into the square? So if you want to apply the context of the bees into this diagram, well, the marbles that Grace is currently moving are the honey. And it's enclosed by the wood, which represents the wax bees have to make. And for those of you curious, yes, the perimeter is equal. It's 90 centimeters for each shape. So we're just about finished here. And as you can see, there is definitely some space at the top left of the square which can be filled with more marbles. And now it's a pretty tight fit in the square. And I'm guessing you guys can anticipate what happens if all the marbles in the square are moved to the hexagon. So let's see it in action. And whilst the marbles are moving into the hexagon, take a moment to appreciate the efficiency of it. It's like nature's golden shape. No wonder why bees choose to use it. It minimizes the perimeter needed and maximizes the area in which you can store things. If only packing for vacations were this efficient. Maybe we should all switch to hexagon suitcases instead. And so now you can clearly see that the top of the hexagon is like what happened with the squares. There's some space left which we can use to fill with more marbles. Thank you, Grace. Now, this shows that the hexagons can fit the most marbles out of the 3 shapes, meaning that it has the most area. Now, some of you guys might be wondering, is there an intuitive reason to why this is? Well, yes, of course. Remember when I told you that the circle has the most area for any perimeter? Well, out of these 3 shapes, which one looks most like a circle? Hexagons, of course. And that is exactly what bees have found through countless years of evolution. And that is probably why you've seen other occurrences of hexagons elsewhere in nature, like the basalt columns near the sea, Saturn's North Pole, the eyes of a fly. But did you guys also know that your own eyes also have this arrangement too? It's the photoreceptor cells in your own eyes, and the reason why they're arranged like this is so that the most amount of light can enter your eye, giving you the clearest image possible. So, the bees and our eyes show how math is actually woven into the very fabric of nature. So while I could spend more time showing you other equations and formulas behind hexagons and other tying concepts which may help supplement it, I don't want to bore you. So I think the bees and our honeycombs show that math doesn't have to be complicated. It's part of nature's language. In fact, just think back to the 2 ways I showed you on how you could approach the problem. The first way, which was a calculation-based approach, might have felt dry, technical at many points. Some of you might have even been lost. But if you compare it with the second approach of using marbles and shapes, it was more intuitive. And hopefully this was the idea that stood out to you because of its simplicity and accessibility. Why does all this matter? Well, it shows you that your experience with math, and by extension anything else, really depends on how you view and approach it. And if you're able to see it, rather than just seeing math as a subject to get A* in to impress universities or endlessly grind on, it can be something beautiful, a language of shapes, art, and symmetry that shapes the world around us. So next time you walk through a garden, or take a run in the park, or even just look out your window, remember that the patterns you see in nature might not be so random after all. If you look a little deeper, you might just find math there, shaping what you see. And to be fair, you don't have to be a math whiz to see it. If we are met where we are at, looking at it from a fresh perspective and being a bit curious, I believe that anyone, yes, anyone, including you in the audience right now, that you can see the beauty in math and how numbers and formulas can look just as stunning as the patterns they help shape. Because in the end, math doesn't have to be mental abuse to humans. For me, it became my approach to happiness. And I hope it can become yours too. Thank you.